Alrighty, folks, hopefully everybody's doing well. We're going to jump into module number 22 here and talk a little bit more about threading and do some examples and just some tracking of information with C++. So this should be a fun one here. So just to give you a little bit of a layout of where we are in the course as we are fastly approaching the end of the semester, we're going to have another assignment that'll be released late tonight, early tomorrow on A9. And we're going to be revisiting our image processing assignment, but now we know about threads, so we will have an idea about how to improve the performance of some of those image processing algorithms that we've written. Okay, so that's what's coming ahead. There's likely to be an assignment 10 as well, but I'm going to be a little bit conscientious about the length of that assignment and so on, as I don't want to have too many, or certainly no new assignments coming out in this last week. So we might have something here, maybe a short exercise or not, but otherwise that's just the range of assignments that we're looking at here, just to give you a heads up on where we're finishing for this semester. And otherwise, I'm hoping to see more folks on the Thursday live sessions. I still want to try to meet everybody in the course. So you can do that this week or next week, just to see where you're at, what you've learned, what you're hoping to still continue to learn as we go on in C++, and maybe if you want to drop some ideas for these advanced topics. Some that have come up have been the Boost library, for instance, maybe talking a little bit about that, maybe some other toolkits, and maybe some advanced algorithms and data structures, doing a walkthrough in C++. So those are a couple of the topics that have been pitched my way, but before we get to that, let's go ahead and dive into today's topic here. So let's go ahead and jump into module 22 here. And this is going to be talking about a topic that's a little bit interesting for a few reasons, the C++ memory model. And I'll get into that here in a moment. Okay, so just to warm us up though, as always, the C++ or ISO CPP website has lots of interesting updates on recent C++ events. So this is a website I love to visit often here on ISO CPP. And on the homepage, usually they're giving the latest and greatest information. In particular, I think ones that are of interest, there's a tool fair here. Occasionally they'll have job postings. The podcasts are usually pretty interesting. This one's going to be sort of relevant to us today. We're going to talk a little bit about memory allocation in threads. And then here's one that's also pretty neat, the 7 top tips for debugging C++. So we've been looking at debugging, and most of our modules have had something related to debugging, but this is just a nice little review here of what we have here. So I'm just going to go to one of these that seems pretty interesting, sort of printing the structures here. And there's little demonstrations to do this. So this particular gentleman in this company, Undo, does a lot of really nice videos on C++ debugging and so on. This is actually where I've learned a lot of my GDB from. So he's actually showing you how to do some of this stuff in which you can actually embed Python into C++ and do some pretty printing there, which is pretty cool. So I'll just leave that link for you here in the description, so you can check out some of these events, podcasts, or whatever other ways make you feel more immersed in C++ as you go forward. Okay, so let's continue on. So last time what we talked about was our introduction to threads in C++. So threads, again, were our enabling data structure, okay? And what threads allow us to do, they are the mechanism which allows us to have multiple flows of execution in our program. And there's a little bit of a difference between concurrency and parallelism. Concurrent means may be happening at the same time, but you might be contending for some shared resource, versus parallelism means happening all at once. Okay, so we looked at a little example with lining up for a coffee machine versus if you have 2 coffee machines and being able to get 2 coffees at once, for example. And this is what we're going to be actually practicing in our next assignment with image processing. Okay, so that's a little bit of what we discussed. And then we looked at several examples just to see what the threading library was available. Again, some people have seen pthreads. Behind the scenes, C++ is probably building on top of the pthread library, but we at least got to see what a basic thread was, what a lock is to protect information that is shared. So the main issue with concurrency is that if we have two threads accessing the same resource at once, then we can get what was called a data race. So we learned how to use a lock to protect that. Then we also learned about async functions and also promises and futures. And then we also did a little bit of other examples with lambdas, so that was a new C++ thing as well. All right, so on to the logistics end. Assignment 8 on splines is out. Again, that's been released. Hopefully that's a good one for folks to catch up on and practice some of their C++. And assignment 9 will be released tonight or early morning, and we're going to be doing some image processing tasks with that. Okay, so the first topic of today is going to be talking about what is known as the C++ memory model. And it's just a short discussion that I want to have with you to let you know what's sort of going on in C++. And this usually comes up when we talk about modern C++. So this is the version that we've been using, right? C++ 17, 20, anything beyond C++ 11. But there is actually a defined memory model, which talks about how we read and write information to memory. And before, we haven't really had to be concerned with this because, well, our programs were just single-threaded. They just executed one statement after the next, if you recall. So if you want, you can read a little bit more of this on the CPP reference site that describes what the memory model is. And basically just defining the semantics of how what it calls the C++ abstract machine works, okay? So the reality is C++ is, compiling down to an assembly language and executing, but there are rules built into the language talking about what memory is and how threads, for instance, interact with and what order of operations take place. Okay, so this is something to be aware of in C++. And the reason I'm bringing this up is because it's an evolving part of C++. In fact, old versions of C++ didn't have a memory model. You just executed your code. If you needed a thread, you launched a thread, you put a lock around it. You didn't really have to think about these types of things. But the Java language actually introduced a memory model, which was a way to formalize how the order of operations take place. Okay? So this page is a nice sort of summary of some of the issues with using threads, and ultimately what computers are doing is you're storing information somewhere, modifying it, retrieving information. That's really it. So this is a way to sort of formalize. And this discussion talks a little bit about what a data race is, for instance, okay? And some of our tools for preventing data races. So for instance, here's an example where we're launching 3 threads that are incrementing this shared counter variable here, and you get what is known as undefined behavior because you don't know what order these threads are going to execute in. Okay? But instead, if you use the atomic, which we talked about, which has a built-in sort of way to protect shared data, then this is okay. Okay? So that is the idea. Okay, so here's what other things that C++ sort of guarantees us for when we have a something that is atomic or otherwise has a lock here. Okay, and this is what is called lock-free. So you can read a little bit on this. This is what is known as, this is a pretty advanced topic in systems. You'd probably see in a graduate level course, talking about how to write concurrent programs without using locks, but lock-free data structures. Super interesting area here. Anyway, this is what I'd like you to know about the memory model. The C language was also inspired and has a memory model as well here. You can see it's not as in-depth, but it does talk about what to do when there are data races or what causes them. Okay, so this isn't a something you have to memorize, but it's just something I want you to be aware of with the C++ language, that it is sort of formalized, and folks have thought about how threads should execute, how this atomic data structure should protect your data, and so on. Okay, so just a few things for you to look at and be aware of. and potentially a candidate for our advanced topic if we wanted to look at perhaps one of these lock-free data structures. Okay, but where I want to go today and talk about some things is again with reading and writing data, and again thinking about it from a threading perspective. Okay, and what we want to do is do another example of just an asynchronous operation, because this is really something that's important for getting performance. Okay, and one way or one example to sort of make sense of this is to think about our file system operations. There's two ways that we read and write data. We do it in a buffered approach, meaning data is moved from some source to disk in blocks, or a stream, or unbuffered, meaning the programmer must manage the data buffers themselves. Okay, so I'm just talking about how we read and write information right now to our system. Okay, and then we have different ways to support in our systems, how we add media, or whether it's plugging in a USB drive, and these are locations that you can read and write data from. Okay, or maybe you put in a Blu-ray disc if you have a disc player at all, a cartridge, etc., whatever it might be. Okay, so if you've done some C programming, or even in Python, or some of these other languages, these functions will look pretty familiar, where you have fopen, fclose, or maybe just open and close. And there's a difference between buffered operations and unbuffered. Okay, again, and this is just your ability to read and write files and how you're doing it when you open it. So buffered means data is moved in blocks. So a buffer or a chunk, if you want to think of this as an array. And unbuffered means, essentially per byte, there's one call to this function. So it's usually pretty simple. You're reading or writing X number of bytes, and it could be as small as just one at a time versus writing a block of memory. Okay, and you can actually see this. Here's a little example for fun, just to see what's going on behind the scenes when you read and write information. So you can run this on the Cori servers, where you have this tool called strace, which will trace all of the things happening behind the scenes in the operating system. And I'm actually going to write this one up because it's interesting enough. So if we SSH into our system here, let's just go ahead and call this hello C. I probably already have one here for a different class. And let's just go ahead and write some of these printf statements here. Printf h, and I'm just going to do these one at a time here. Hello, like this, okay? And then I'll put the new line character, and other C function that you can do is you can force whatever you are accumulating, these pieces of text here, the characters H, E, L, L, O, and so on, then you can actually flush out that buffer and do your write call, okay? So let me actually just compile this here. I'll make it a little bit bigger just so you can see for our hello.c program. And I'll just output it as we usually do. Let's make sure it works. Oops, /program. So hello, works fine. But the strace tool is a way that we can see all the system calls that happen behind the scenes. Okay, this is what your operating system's doing. This is how that work is actually being done with these very primitive operations. But if you look down here, you'll see that there is actually just one write call, and the printf function buffers these things up until it flushes. Okay, that flush command is called. Okay, so you can see the one write here for 6 characters and the string here. Okay, so it's kind of interesting to know about how some of this stuff works here. Now, when we're doing some of these operations, we can do them in a way, so if I'm just writing out information or perhaps reading information from a file, we can do it synchronously or asynchronously, okay? And this is getting into the threading part. So again, synchronous means that there's some sort of ordering that must be enforced, okay? So we want to do this sort of reading or writing of information from files. Okay, so here's an example where we're reading a file. And when I make this call here, this fread, so I'm just reading in some amount of bytes here, however many, let's say the buffer size is 500. I'm just reading 500 bytes of a file. Or let's say it's 5 million, something really big, or 5 billion. Then we're blocked here waiting for that information before we can make any progress towards the rest of the other stuff going on in our program. We are blocked or halted at this point. Okay, so what we really want to do, however, is do something, especially with file operations, of what's known as asynchronous file I/O. Okay, and let me bring you to an example that you probably care more about, or that I care about, I guess, certainly, because this video is on YouTube, and if you've ever seen, when this progress bar is loading here, you'll see the red is the data that's been loaded, or where we're at in the play, excuse me. The darker gray is the data that's been loaded, and then the light gray is the data to be loaded. So this is the buffered data that's been read in and is ready for us to read from and display the video here. So YouTube's a great example of this. Now, how is it working though that we don't have to click this play button and wait for the entire video to load? Because that would take a long time, right? These lectures range between 30 minutes on the short end to maybe an hour and a half or an hour and 15 minutes at the longest. You wouldn't want to wait until the whole video got loaded. You would want to be able to start watching the video and have the video streaming in, okay? And this is what we can do with our asynchronous calls in our thread, which read some buffer of data and load it in, okay? So this is something that we should be worrying about. We could just use the C standard library or whatever's given to us in C++, which is built on top of some of these C libraries here. But we really want to be able to have control over when we're reading information. So I want to spend some time doing a little bit of live coding here to demonstrate this asynchronous loading of a file. Okay, so this is a new feature again in C++. We saw it briefly last time where I used async, but this is a more sort of motivated example, something that's very important, I think, today for getting performance. So I want to live code this one. And yes, for folks who maybe have used Boost, we've had a few in this class who have, the majority haven't. There are other asynchronous libraries out there for doing some of these things, but I'm going to show you how to do this stuff from scratch. Okay, so here's our example. I'm going to just live code it. Okay, so let's go ahead and start from scratch here and build up an asynchronous example where I show you how you can do something in the background, okay, while your program is still running. Okay, and this is a super powerful idea that we can make progress in some part of our program while the other program is just loading some data. Okay, so first thing that I'm going to need to do is include the thread library here, okay, because that's what we're going to be working with. And I'm also going to be wanting to use our futures. Okay, this is how we do something asynchronously. This is where our async comes from, and this is where our threads come from. Okay, and I'm also going to use a few other libraries for us, like potentially a string library here. I'll just go ahead and include it now. Okay, so where do we want to start with this example? Well, we're going to want to create some sort of future here, okay? And we can do this by either, sometimes we can just use auto, which is another new thing that we learned about, but I like always typing out the type name. And I'm just going to call this my future here, okay? And what our future is going to do, remember, this is the thing that's calling some other function and going to return its value when we need it, okay? So what's this going to do here? Well, it needs a function to call. So we want to be able to do something in the background. And I'm going to go ahead and do something like a file loading example. So let's just say we're loading a really big file. It has some file name here. And this simulates loading a really big file or piece of data. Okay? So this could be our YouTube, for example, where we're loading in a really, really big video. Just to give you an idea, these recordings that I do are usually 3 or 4 gigabytes in size because they're in high definition and so on. So something really big like that. And we might want to do something like, let's just track the bytes that are loaded, okay? So again, this will sort of simulate what's happening. So bytes loaded equals 0, and while our bytes loaded, let me rename this to loaded, is less than 10, let's go ahead and just print out a message here so we know what's going on. Loading file. Okay. And let's print out the file name. Okay. And I'll put a okay. And just to simulate what's going on here a little bit, we can put this thread to sleep. So put a pause or halt in our thread. Okay. So how I'm going to do this is there's a function here. So again, looking in our thread library, it's standard. This thread, it's kind of an interesting name. So the current thread that's executing this function, we just want it to sleep for some amount of milliseconds. And now how do I specify the milliseconds? Well, I actually need a library for this, the time library, which is Chrono. And let's just say 100 milliseconds should be fine. So we need the time library now, which is called Chrono, time library. Okay, so we've got this much so far. Let me go ahead and compile it and see if I've made any mistakes. This is about the appropriate amount of code that I want to write before committing. Okay, so one return value here for my function, and let's just go ahead and return true here. Okay, so this will run. It won't do anything yet because our future hasn't been assigned. So we want to assign our future to some thread that we're going to create, and it's going to execute asynchronously. Okay, so how do we do this? With async here. And we can specify, we don't have to do this. It's going to do it by default, but we can say it launches asynchronously. Last time we just put in the function name here, but I'm going to show you, as much as I can here. So let's just go ahead and type in that we want this to launch asynchronously, just to be very explicit about it. And what's the function that we're going to launch? Well, it's going to be called file loading. And the argument is going to be my really, large data set. Okay, whatever it's going to be, .txt. Okay, so that's, again, simulating, this really large data set here. And I want to actually make sure I terminate this loop. So let's make sure our bytes loaded plus equals. Let's make it a little bit more realistic. Let's make it like 10,000. It's loading 1,000 bytes at a time. Okay. So this is going to launch asynchronously, and this is going to happen in the background. So this launches asynchronously, and will happen in a background thread while our program executes. Okay. So again, all this function's doing is it's looping until it loads the whole file, and we're just simulating this by putting a little loop here, and then we're putting it to sleep every 100 milliseconds. So every 100 milliseconds, it's going to load 1,000 more bytes. That's just simulating how long it would take to find information on your hard drive until we've got 10,000 bytes loaded, and then we report back that, yes, our file has, in fact, been loaded. Okay. So meanwhile, in our other program, we can just do whatever we want. So meanwhile, while our program executes, we do other tasks. Okay. So often we'll find this, just like our SFML programs, where we'll have some task that's going on here, and our program will just run for a while. And I'm just going to create another counter here, iterations, and let's say while our iterations is less than 100, we will also just print here something. Okay. The program is running. Okay. And let's put a little printout here. And I want to increment this iterations here. And let's also put this program, our main thread, to sleep here. Okay, just for 100 milliseconds at a time here. Okay, so let's go ahead and run this and see what happens. Let's first see if I made any mistakes. Luckily not. And let's run it. Okay. And we see what's going on here is, our program's running. It's going to print this out 100 times, and then it's going to complete here, okay? But what was really interesting is, let's see what happened at the start of this program. Let's see the asynchronous part here. So from when I launched my program, it said, okay, program is running. So it actually jumped all the way down here, and this thread was launching asynchronously in the background. Okay, so while our program was running here, you're going to see interleaved loading file, loading your large data set, loading the file, loading the file, loading the file, but your main program's still running. It's still printing out these messages in between here, okay? And this is the real power of the asynchronous function call here. So this is what I really have to emphasize for you folks here. I'll put myself down here. That this ability to be running our main program in the loop over here on this side while doing something else concurrently. I think this is the example that'll make maybe the concurrency part hit home as to what's going on and why writing programs that take advantage of this asynchronous functionality is super, super powerful in C++. All right, so let me go ahead and just rerun this one more time. And I'm going to actually just decrease the iterations here and increase the wait time just so you can see things happen a little bit slower here. Okay, and let's actually up our loading file here. Let's make it a little bit longer here. Okay, so I'll have to recompile because I've made some changes, and we'll rerun our program. Again, it's going to immediately start the loading process here, loading this many bytes at a time. So this is what happens when you load a YouTube video, for example. There's some other background thread constantly loading data. And then the main player starts reading that data that's been read and processing it one at a time. And I've artificially put in these sleep commands here just to simulate how long it takes to load the data or our program to run. Okay, so again, we can see our program is running and it's intermittently loading the data set here. Okay, every 1 second our program is running, but you see the interleaved calls here. Okay, we could probably balance this out just to make it a little bit more, again, interesting, just to get about the right ratio. But again, this is what's happening with the asynchronous functions here. Okay, so every 4 seconds you're loading about 4,000, or excuse me, every 1 second you're loading about 4,000 of the bytes, and then your program is proceeding. Okay, so this is the idea with asynchronous I/O. Okay, so let's go ahead and return to our slides and just recap. Here was our file. Here was the program that we launched here. And we wrote the asynchronous function, which is a future. So that means we're going to get the value in the future for this function. So we can either explicitly call .get like we did last time and say, hey, we want this immediately. Or if it's an asynchronous function that's just going to be launched and processing information in its own loop and doing some other task, then we can just launch it asynchronously like this. Okay. So here was our main. We had our function here called the future. This is the asynchronous portion for how we're going to execute this, how we're going to launch in the function that we're launching, which is called file loading. And then, of course, here was our function that we're actually loading the data to some shared structure or performing some other computation. Okay, and this is the idea. Okay, and we're just simulating that every 250 milliseconds or so, some amount of data is being read to the disk. Okay, so again, as a reminder, a thread is a separate process or execution. It's a lightweight process that's running within our main program, and it has its own logic or control flow to achieve some task. Okay, so roughly, regarding to the number of cores that we have, so maybe if you have 32 cores or more, you can execute 32 of those functions asynchronously, roughly speaking. Okay, most of your machines have 4 cores. They usually look like this, and here's sort of the visualization of your chip here. So you can do 4 things asynchronously. Okay, so here's just another example of doing the asynchronous loading here. And here was our output. Okay, so with that said, we're going to take a little 5-minute break if you need, and then hop into another example to show one of the sort of dangers of threads in a sense. All right, and if you've taken a little break here, I want to pick up with showing an example of how we can, or one of the things that we need to think about with a thread here. And this has to do with tracking memory that we allocate, okay? So for instance, every thread that we execute is going to allocate some memory, okay? And it's going to clean itself up. It has its own stack memory. But we do have to be careful if within a thread, if we allocate new memory using the new operator, that we also reclaim that memory in the thread. Because once the thread's gone, it's gone away. There's no way to get back to that flow of execution. So we still have that issue, just like when we called functions. So the good news is I don't even need to use a thread example for this, but instead I'm going to set up another example for showing you how to track memory. So regardless if you're using threads or not, we'll want to understand how we can just track memory to see if we're losing it anywhere. And the reason I'm bringing this up now is because, well, we've talked a little bit about the operator overloading ability and our ability to do that with the plus operator, for example, when we were doing things with the copy assignment operator with also the equals operator and so on. But we can actually overload another operator called new. So I'm going to go ahead and set that up here for us. All right, so here's a empty program for us, and which I'm going to show you how to overload the new operator so that you can track what's happening in your program. So again, let me show you what the issue is going to be. If I have some function here called foo, and I go ahead and within here allocate some memory here, and I say new, integers 1000. Recall that as soon as I leave this function here, this pointer goes out of scope, and I've just allocated somewhere in my operating system 1000 integers. I need to delete this memory before I leave the scope of this function here, okay? Otherwise, I'm going to get what's called a memory leak. So what we're going to do is build a way to track our memory here by overloading the operator new. And this is a really handy technique that you can use here. And it's actually quite simple. You can do void star, that's the return type, operator, and the operator that we're going to be overloading, whether it was plus, minus, whatever it is new. And new takes as a parameter the size of how many bytes that you want to allocate. Okay. Now, where do I find this information about new and what type of function it is? Well, I'm going to go to CPP reference, and I'm just going to type in new here and search for it. And we'll see the operator new. That's the second one here. So you can see what the function signature is, and this is what we're going to override in our program for how we allocate memory. And this is a way of us sort of building our own sort of memory allocator. Now, for folks who go on to take systems with me or another class, you'll actually do this and see how to manage memory. We're going to build a little bit of a cheap memory allocator here, and mostly to be able to track our memory and understand just what's going on in our programs. I think this is a really nice insight into one of the powers of what C++ can do. Because one, we can do the operator overloading, which I'm going to show you how to do here. And two, we can build some infrastructure around how we keep track of the memory that we've allocated so we can find any bugs in our program. Okay, so let's go ahead and take a look here. All right, so we've got here our operator here, and this is the signature of the function that we're overriding. Okay, so I'm going to go ahead and back to our code. And all I want to do for now in this function is, let me just go ahead and print out bytes allocated and the size. Okay, that's what the parameter is, and the operator that we're overloading is the new. And this is a little bit weird because usually when we talk about operators, we think of things like plus, minus, divide, multiply, etc. But new is actually an operator, and that is something that we can override. And in fact, we can also override delete as well. So we're going to want to do that one too. Now the question is, how do I actually grab memory now that I've overridden this operation? Well, what I'm going to do is I'm going to just return from the malloc function the size or the number of bytes that I want to return here. Okay, so let's go ahead and call this function here and do an array of ints and new, and let's say we have 1000 here. Okay, And let's go ahead and compile this program. I'll do it like so. And we actually don't need the thread here for this particular example, though the same example would apply regardless if you're using threads or not. And let's paste it in. So that runs. And now when I run my program, you're going to notice that every time that I do new, it's actually going to figure out what the size is of this data type and say 4,000 bytes were allocated. Because the size that we are requesting here from new is the data type, an integer is 4 times 1,000. And that's pretty cool that it just works there and tells you how many bytes that you've allocated. Now, we would also probably want to keep track of how many bytes have we freed as well. So let's go ahead and write or override the delete operator here. Okay, so it's going to look similar to this. And let's go ahead and it's the operator and it's delete. And we're going to have the pointer to the memory that we are deleting, so whatever it is, and the size of the bytes here. Okay. Now, this is where things get a little bit weird because you might have noticed that we're using malloc to do the memory allocation, which is a C function. And that's okay. We don't have to worry about doing, for example, the delete with the brackets or delete here when we're overriding new, because we're saying we're going to use this different memory allocator to grow us our memory. Okay, so when I'm doing delete here, I do want to specify the size of the thing that we are deleting, or how many bytes here, at least in this allocator. So bytes being freed. Okay, and the memory that I'm freeing is just memory here. So let's also try calling our delete function here. Okay, so let me save this, clear this guy, and then add in delete. Okay, so how do I know how to do this delete, or again, how to do this operator delete here again? So again, I've searched for operator delete, and I can see the different signatures here. So if I want to do something that's going to delete a block of memory, well, I'm doing the override for operator and delete, and then something that takes in the size here. Okay. So in this particular instance, this one here. Okay, so it takes in the pointer that we want to delete and the size. And I'm just going to use it like I normally do, and it's going to work just fine. So I'm just going to do delete, and because it's an array, a bracket, array events. And let's go ahead and just make one small change just to put an end line here, so that we can see what's going on here. And I'll go ahead and recompile this, rerun it, and we'll see the bytes allocated here. But no call to delete. Well, that's again because I have to be careful with the delete that I'm using. Again, I have to do the operator for the brackets here, and this is the one that I want to override. So let me actually copy this function. If I just call the one delete here, actually, let me show you this before I fix our program. You'll see that the bytes being freed is only 4 here, which is why we have to use the brackets here. Okay, so let's go ahead and just override this one here and do the operator delete, like so, recompile, and this time, let's see if we get 4,000. Okay, delete, bytes allocated, 4,000. So it's still not calling the function in this way here. So one more fix that we would have to do. And again, that's just looking at our operators here. Actually, just do the one without the size here, and that should call the appropriate operator here. Because when we're deleting, we don't have to specify the amount of size. We're just freeing the memory here. Okay, so that means in our print, we're not going to know yet how many bytes have been freed. It's just going to say that it's been freed. We know that the pointer is being freed here, and in C you just have to specify free, and that'll get rid of everything. But how would I know or want to know, how many bytes were actually being freed? Well, in order to do this, we would need to create some sort of map data structure here. So we could include a map, for instance, and let's just go ahead and I'm going to get rid of this here, and let's see. Let me just go ahead and create a global map here. And it's going to consist of a integer here, uint 64t, and a number for the amount of bytes that were allocated. Okay, and this would just be our memory map here. Okay, and it's a global. So every time I allocate something, I would need to also mark the address will be the input, that's the integer, and then the size of that allocation. So let's just go ahead and try this out and see if this works here. So our input's just going to be the address, and it's going to be the size here. Let's see if that works. Oops, it doesn't like size t here. We could just go ahead and use the pointer type here. Let's see if it likes this here. If I just go ahead and put in whatever the pointer is that we are getting here. So I'm gonna have to refactor this a little bit here. So our memory that we're granted, that's what we have allocated. That's what we want to return. And in our map here, we want to actually just put memory as our key here. See how that does, and there we go. So now whenever we're freeing our memory, we look in the map, and then we would also have the size of that memory here. So let's go ahead and just make that little change here. So right before we free, we'll look at our memory map at whatever the pointer is that's coming in, and we probably want to store the addresses of these pointers. So let's see if this works here. Oops, yeah, this is giving us some interesting. Now it's giving us some interesting errors because it's when we're allocating here, we're also allocating when we create the memory here, and that's triggering another allocation, and so on. So we have to be, I guess, a little bit more careful with this allocator tool. And instead, we would have to go and maybe not use one of these structures, but instead just use a array or something more simple that has a fixed size sort of allocation. So this is an infinite recursion. This is actually kind of neat here that you can't because this is newing within it. It's just going to keep newing again. So that was the issue here. So I would need to malloc for this, but anyway, that's the idea here, that you would have to have some sort of memory map here. And let me just do a really simple one here, just to show how we would do this here. We would have some array, and we can keep track of the allocation number, or again, use malloc for our map that we're creating. Actually, I don't want to dive too much into this because this is building a allocator sort of from scratch, but that's the idea. You need some sort of map to show how many bytes are being freed. Now this is the way that tools like Valgrind, for instance, are implemented. So rather than implementing this and worrying about some of these corner cases of these sort of infinite recursion, I can show you a really valuable C++ tool here. Okay, so what I'm going to do is I'm just going to comment this out for now. And I'll comment it out so that it's the working version, so we can't print out how many bytes are printed out. But instead, what I'm going to do is, let me recompile this program and run it. Doesn't do anything too interesting. I'm going to run it through a program called Valgrind. So for folks who are on the virtual machine or Linux, and you can set this up for Mac as well as Windows, this is a way to check your memory errors. And this will work for threaded programs or regular ones. But when I run this program, what it does is it checks to make sure that all of the memory that I've allocated has also been freed. So I've done 2 allocations and now 2 frees here. So likely there's some other allocation going on in the background. But let's see what happens if I forget to delete my memory here in its scope. Okay. So if I run Valgrind now it definitely identifies that 4,000 bytes were not freed here. Okay. And that's what the tool is doing. It's overloading the possible functions that could be called for allocating memory, building some map of it, and then tracking if that memory, by the time the program exits at line 39, has freed all of the memory. So again, because in C++ we're working with managing our memory, this is something we have to keep in mind. Because C++ has this memory model, just to bring things full circle, we are able to build these tools on top of it and make sure we don't leak resources. So again, this is a little bit of a technical lecture in System-Z and C++, but again, showing what is built into C++, why it's, again, a powerful language, and some neat things that can be done. Okay, so with that said, I'm going to end things here, and we will move forward. So I hope learning about this tool, Valgrind, will be useful for your future C and C++ works. You, again, understand that there's a memory model and the importance of asynchronous I/O so that you can write programs that are faster and in some ways also easier to maintain once you understand the structure of the program.